Hello, in this problem we will be graphing a rational function using its asymptotes and its intercepts and its derivatives. So, first of all, starting with the intercepts, the x-intercept, of course we're going to set the whole equation equal to 0. Of course, the denominator will multiply over and cancel out. And we're left with x squared minus 4, so x would equal plus or minus 2. For the y-intercept, we'll plug in 0 for each of the x values. So 0 squared minus 4 over 0 minus 1, and we would get the y-intercept is 4. Another easy one is going to be our vertical asymptote. I'll just go ahead and abbreviate that, VASI. And all we're going to have to do here is set the denominator equal to 0, and we will get x is equal to 1. Okay, now things will start getting a little bit more complicated. Notice here that we're not going to have a horizontal asymptote because the power of the numerator, or the order of the numerator, is higher than that of the denominator. Notice the highest power here is 2, the highest power here is 1. When that's the case, we're going to have a slant asymptote. Remember, when they're equal to each other, the order is equal to each other, and then we'll get a horizontal asymptote. So here we're going to have a slant asymptote, and in order to figure out the slant asymptote, we actually have to divide these polynomials. So we're going to have to use polynomial long division. And because there's no x term, I'm just going to put a place filler in here, 0x minus 4. Okay, so the question then is, how many times does x go into x squared? And that would be x times. Then we take the x times x minus 1, get x squared minus x, and we have to subtract that. Notice we subtract the whole thing, so when we subtract the negative x, that turns into a positive x. So we get x squared minus x squared is 0, and 0x plus x equals an x. And then we'll bring down the negative 4. And then the same question one more time. How many times does x go into x? And that would be positive 1 times. We could figure out what the remainder is, but for the case of our slant asymptotes, that doesn't really matter. So we get x plus 1, so that would be our slant asymptote. Okay, now that we have our slant asymptote, we can go ahead and start taking some derivatives in order to determine things like when is our function increasing and decreasing, and where is our function concave up and concave down. So, taking the derivative, we do low d high because we're using a quotient rule. Low times the derivative of the top minus the top times the derivative of the bottom, which is 1, all divided by the bottom squared. Now I did some of this work ahead of time just to make the video go a little bit faster. You're more than welcome to double check this on your own. But this is going to simplify to x squared minus 2x plus 4 divided by x minus 1 squared. And then we set that equal to 0 in order to figure out where our derivative is equal to 0. So this is the same as setting the numerator equal to 0 as before. And actually, this doesn't give us any solutions. You can double check that with the quadratic formula if you want, but x is never equal to 0. But again, what was the point of this? Well, we're trying to figure out when is our function increasing and decreasing. So I like to use a number line, and what we normally do is on the number line we throw in any values where x was equal to 0. In this case, that's nowhere. But for rational functions like this one, there is actually one exception to this rule. Whenever we have a vertical asymptote, we'll actually want to test around that point as well, because the interval, it could change from increasing to decreasing after the asymptote is y. Okay, so we know that our vertical asymptote is at 1, so we'll check to the left and the right of that. So, for example, we'd plug in something like 0, and if we plug that into our function up here, we get a positive 4 over a positive 1. So we would know that's positive, and our function is increasing. If I plug in 2, which is to the right of 1, I'd get 4 minus 4. I'd get another positive 4 divided by positive 1 again. So I would get another positive. Okay, so our function goes from increasing before the asymptote to increasing after the asymptote. So we'll make use of that later. And finally, we need to take the second derivative to figure out the intervals of concavity. So again, we'll use the quotient rule now on the derivative. And so we get low times the derivative of the top minus the top times the derivative of the bottom. The derivative of the bottom, notice we're going to have to use a chain rule. So the derivative of the outside is 2 times x minus 1 times the derivative of the inside is just 1. And then divided by the denominator squared. This one takes quite a bit more time to simplify, but again, I will let you do it on your own. And when you do simplify it, you'll get negative 6x plus 6 divided by x minus 1 to the 4th. And so we see that our second derivative is equal to 0 when x is equal to 1. Okay, now we'll do the same kind of chart with our second derivative. Remember, we have to test at any point where our second derivative is equal to 0, as well as we have to check our vertical asymptote. Fortunately, those are both the same number in this case, which makes things easy for us. Okay, so again, now we'll plug in 0 to our second derivative, and when we do that, we will get a negative value. So that's telling us that we're concave down, so like a downward shaping bowl like this. And if I plug in, if I plug in 0, I would get a positive 6. My apologies. So an upwards facing bowl. But then when I plug in a value like 2, then I would get negative. And so I get a downwards facing bowl. Okay? Now, that's a lot of information, but I will now show you how to use all that information in order to graph our function. Okay. So let's go ahead and start by putting in our intercepts. If we scroll back up to the top, we see that we have x-intercepts at positive and negative 2, and a y-intercept at 4. So negative 2, positive 2, and then our y-intercept at 4. Then, I'll go ahead and throw in our asymptotes. We have a vertical asymptote at x equals 1, and a slant asymptote at x plus 1. All right, so here is our vertical asymptote. And then here is our slant asymptote. Okay? Now, we finally just have to use some of this information. Well, our derivative told us that our function is always increasing. So it should always have a positive slope. And our second derivative tells us that until 1, we should have a, it should be concave up. That means, of course, it can't be in this region because that would be concave down. So it better be in this region here. And that makes sense too because it has to cross through those intercepts. So we do kind of see an upwards bowl here. It really follows the asymptote for a while, but it looks more like an upwards bowl after you get past 0. And then we know that this one has to be a downwards facing bowl passing through the x-intercept too. So real quick, let's just verify that it does meet the criteria of our derivative and our second derivative. We do see that our function is always increasing, and we have an upwards bowl until 1 and then a downwards bowl after 1. So all of that information is contained in our function here, and that's approximately what it would look like.